Afternoon. I really appreciate getting the time right after lunch. I try to talk with a melodious voice and put everybody to sleep. So I'm VP of Engineering at Qualcomm. I've been there about 3 years now. And I have the honor of being responsible for all our GPU technology from a hardware standpoint, and in part some of the software, like the compiler for GPU. This presentation has to be brief. It's a 15-minute presentation, which is usually how long I take to introduce myself. But I'm going to focus a little bit on the background for Qualcomm GPUs and give you a little bit of a setting, then talk about how OpenCL fits into our roadmap, then some of the cool things we've been doing internally with OpenCL and GPU Compute, or just say heterogeneous compute in this case, and finally some of the developer resources we have available. Just in case you're not familiar, Adreno is just a trademark we use for our GPU to define the family of GPU products. Now, this is a corporate template, so sorry about that. Just a few things I wanted to highlight on there. So we'll be celebrating 30 years in July. I don't know what kind of party. But if you really look at it, building SoCs with GPUs is actually something fairly new for Qualcomm. It's only been about in the last 10 years that we've been building that. And this 15 billion unit, I wanted to highlight that because that's actually a very back-end loaded thing. We're getting close to shipping 1 billion, not quite there, but we're getting close to shipping 1 billion chips a year with GPUs on board. And usually they're all in SoCs shipping into the mobile space. It is a gigantic space. And we're seeing a lot of interest in our products. And it's just a magnitude bigger than anything I'd been used to seeing in the past. If you look at that as market share, I just took the John Petty's latest December numbers. And this is not a bragging chart, but it is saying that these large numbers of GPUs are shipping into the mobile space, and they're representing a fair amount of that market. And nearly all of these are running OpenCL and doing very well using GPU computes with either our customers or using GPU compute for our own internal purposes. That ends up going through our customers. So let's talk a little bit about our roadmap. When I joined about 3 years ago, we were on our 3rd generation Adreno products. Every 2 years or so, we tend to switch. And that was the first introduction for us with the Snapdragon S4 Pro of OpenCL. We did an OpenCL 1.1 release at that time. And since then, this 3rd generation has been fairly popular. And we've continued to have OpenCL 1.1 embedded available. With our 4th generation we just introduced, we switched to OpenCL 1.2 full profile. We don't have any religious belief of embedded versus full profile. It's 2 simple reasons for us. One is cross-platform compatibility. So when a lot of our customers are moving from, let's say, a development system on PC or from another platform of some sort, moving to a full profile for them has been something that is a lot easier. The other thing is larger memories and some of the other advantages of full profile are good. Going forward, I'm not going to promise we're going to be full profile across the board, but right now, for most of our tiering, we are moving towards a full profile kind of environment. It does seem to ease the compatibility level, at least in the 1.x time frame. So looking at some of the things we're doing, obviously our customers, and I think Imagination quoted that this morning, a lot of our customers are using OpenCL. In fact, most of our key customers are using OpenCL. And by customers, I mean the OEMs that make the phones, are using OpenCL today, for example, in the camera pipeline, as was shown this morning, video post-processing pipeline, lots of other applications. I tried to get permission to talk a little bit about that, but I couldn't quite get it. So we focused on what we're doing. And we don't look at our internal research as anything that is going to be directly applicable to the end user. We're all doing work that enables the platform so we have good solutions, but that we enable our customers to deploy solutions based on these things. So one of the first things to highlight is an accelerated library. We have a CPU, DSP, and GPU accelerated FastCV. FastCV is our internal version of like the OpenCV kind of foundation library. It's a lot of computer vision algorithms. It's hundreds of different functions. And some of them have been ported to, well, most of them have a CPU model, some have a DSP model, and quite a few have a GPU model. All of our GPU is based on OpenCL. And you may ask, why do you have all three? What we found is that depending on the power profile and the performance needed, different heterogeneous cores deliver different qualities. Certainly, the CPU tends to be easiest to program and get stuff off the ground. And in some cases, especially the vector versions of ARM processors, it does a fairly good job, and it can be turned on, turned off very quickly. DSP excels in very low power cases like voice recognition, being able to wake up your phone so the DSP just wakes up a little bit. And image processing, heavy, that kind of stuff tends to work really well on the GPU. So we've actually partitioned the library across all of those. Another one, obviously this is a sub-theme of, of this presentation. I think I've seen everybody talk about CNN or DNNs. We have two research teams at Qualcomm, both in our corporate R&D and as well as in our multimedia R&D, that are actually doing a lot of research there on convolution as well as matrix multiply deep learning. And they've been using both CPU and GPU. What we've seen, and I won't claim we're experts, but what we've seen, generally speaking, is about a 2x performance per watt advantage on the GPU versus a CPU. And that's taking a CPU and a GPU that's sort of in our premium tier. And when I talk about performance per watt, I will honestly say that's all that really matters for us, right? When we're looking at a mobile device, even a larger one, this is about a 3-watt form factor. That's total SoC power, including PMIC, so the power supply for it. And even now, the thinner ones, like the iPhones and other, the Galaxy S6, are even thinner with even shallower power profile. For us, it's really about performance per watt. So when we look at these convolution, it's really what can we do in these bounded power envelopes? And can we get to modes where we can do this real time, for example, using whatever component of the heterogeneous platform we can. So we're still early. It's about a year into our research there, but we've shown some really good stuff. And I have some numbers. I don't know if I have numbers here, but we were able to show, at least in a Snapdragon 805, for example, that we were able to achieve about, it scales very well to multi-core, but we were able to achieve in an Adreno 420 core about the same performance as two CPUs and half that power. So for us, that was a really big ability. And we were measuring things in sub 30 milliseconds. So we were considering that close to real time in some of these image recognition patterns. We did last year, and we demoed some of this, 3D scanning, being able to take your phone, move it around, wave it around, and capture an image, and actually being able to reconstruct a person with both the textures and the volumetric geometry data underneath that, all done on the GPU. And these are some of the, I guess the projector is not very friendly, but this is fully rotatable and playable as a captured image. We just demoed at CES in January this car demo where you have 4 fisheye lenses in all 4 areas of the car, front, back, side, left. And they're all fisheye, so you get a fairly wide field of view. We're able to take all that information and then generate either a bird's eye view or effectively a spherical texture environment map around that car. And you can fly through it or look at it from inside the car. So you can get a real sense of what's going on inside the car. And Arthur, was this on a 805? I think so, right? Yeah. On an 805, we were getting 30 FPS on the GPU, and we were getting about half of that, about 17 FPS on the CPU version. So we were getting real-time performance running on that Adreno 420, which was not our top of the line, but fairly good GPUs, all within the power envelope of a mobile device. So this kind of stuff is fairly cool for us. And all of this was written in OpenCL. Another demo, and you may recognize Arthur or not, based on how dark that looks in the audience. I actually saw somebody present this morning a little bit about this, but again, this is a popular one. Being able to isolate, for example, foreground objects such as a person, and being able to isolate them from their background, and then being able to low-pass filter your background to reduce the frequency information, as well as to be able to actually either remove that so that no distractions occur, or or just keep it in a low refresh mode so you don't have to update it frequently. So obviously in video conferencing this is very, very interesting, but the idea there is to focus all your bits in your foreground and then reduce the amount of distraction and bit rates required for your background. Able to do that on that 805 core at 33 FPS versus the 17 FPS using our 4 32-bit Crate 4s that are in the Snapdragon ARM v7 Snapdragon CPUs that we have on here. So again, it's not just about performance, though in this case it also delivers performance. It's really about performance per watt. We actually were able to do this in a lower power envelope, far lower power envelope than a CPU. It's very typical that if you actually power up 4 ARM cores on a mobile device, you will not be able to sustain that for a very long time in a mobile device. You'll hit a thermal limit. Let's say your skin at 39 or 40 degrees C will just cause throttling. If you're able to move that all to the GPU and run it there, you've created a much better user experience because you won't get that weird performance drop-off. And you'll get much higher performance in this case. All right, some of the tools. Yes, you can read. So developer.qualcomm.com, though I'll have another slide at the end that recaps this. We have a lot of resources available for developers, both our OEMs as well as our ISVs, partners that we work for. And these are all available for download for free off the website. So we have a lot of documentation. We have the SDKs available. We have videos. We have a lot of the source code for a lot of the stuff we're showcasing, either coming up or other work that we've done. I know we have OpenCL reference codes for a lot of different stuff. And this is always expanding. There's always more work that you can do on here. We were talking recently about putting optimized code for example, matrix mulls and so on. We have some of that that's going to go in. So there's always a lot more work that can go into here. But this is a good basis for our developers. We also do have an on-device OpenCL debugger. So you're able to plug in your USB device. Most devices work. Plug your USB device and actually profile not profile in this case, but debug your application running. And you can actually simulate single stepping through it. And you can do a lot of stuff that you would want to do on an OpenCL kernel using this debugger. We also have a profile, both a static one and, well, I guess the static one is the kernel analyzer. The kernel analyzer will actually compile kernels and gives you back statistics on, for example, number of registers you're using, number of ALU instructions, and so on. So it's a good sort of quick and easy way of judging the quality of a kernel and what likely performance you're going to get out of it. But we also have the profiler and tuner, which actually gives you in real time what's actually going on the device and gives you performance information. I believe also has a power hookup so you can get a sense on a specific device what the power profile is going to look like. These are tools that continuously are changing. In fact, I recently saw our roadmap, and there's stuff in the next 2 years that is going to continue to improve here. It is, like we discussed a little bit yesterday, there's a little bit of chicken and egg between having the hardware, having these features, and the debugger reflecting all of that. I'm a big believer in the chicken part of that, but as it goes forward, we do expect all these tools to get better. We want to have more heterogeneousness to them, so you can do CPU and GPU profiling, for example, simultaneously. And then as the hardware develops, hopefully hooks, so you can get more information about what's going on inside the hardware, as well as more debuggability in there. So they're good now. They're going to get better later. So on the OpenCL side, fundamentally, it is our basic compute GPU commitment inside Qualcomm. Now, obviously, a lot of our customers are using OpenGL, whether 3.1 or even 3.0 as a compute language. Obviously, on Windows, they're using, not sure what they're doing on a DX9 device, but on a DX11 device, they'll use direct compute. And then there's render scripts. So there are different alternatives, and different customers may choose to use one or the others of that. But internally, and towards a lot of our OEMs, OpenCL has become our primary GPU compute language. It's always tricky to try to expose it all for ISVs, but definitely OEMs get first dibs on getting all of that. And it's all about, a lot of the cases, it's about performance and power, right? Can they implement something, whether it's in a camera pipeline, whether it's in a video codec pipeline, whether it's in image processing, I mean, any of these things, can they achieve something using OpenCL on our GPUs that actually allows them to differentiate? And the answer has generally been yes, because this allows them very good low-level access to the hardware and very quick development. It can be moved from desktop to the mobile platform if need be. We've seen a lot of people do some pretty amazing things on the mobile platform, and running them on the GPU using OpenCL has really allowed them to achieve performance levels that they wouldn't have been able to on the CPU. So we've seen it as the outcome, by the way, is better user experience, right? If your camera does something fancy, that's a definite better user experience. If it's faster performance, if your latency of having computational photography come up, and all of these things translate directly to user experiences that are improved. So 3 things. I think I'm okay on time. 3 things to note here. First of all, we do have reference design. So a lot of our folks either can develop on a off-the-shelf kind of design, or you can use a reference design, particularly for new chips if you're looking at a new design. And that's available from Intrinsic. We also have all of the stuff I talked about available for download. So that's fairly straightforward as well. We also have our support forums. So we have these are actively supported support forums, both user to user as well as professionally supported. So there's a lot of discussions that go on there. And finally, Arthur volunteered to give his email out. I don't know how wise that is, but it's still a fairly small group, so don't go sending it out to your friends. But a lot of the work I showed is still early in our case, and we don't intend to make it as an end product, but we do want to share with people that would want to turn it into an end product some of the outcomes that we're doing, plus some of the other research that we've done in the past that I didn't highlight here. So he's a great reference for a GPU, as being our GPU product manager as well is a good thing. So he's always a good reference for a lot of these questions. Speaking of which, I think I'm still okay on time, and I'm willing to take questions.
So do we have any questions? Yeah, let's thank our speaker.
So you're working on a layer called Mare. Mm-hmm. Could you elaborate on the plans for Mare?
Okay, I don't need the mic. Yeah, so Mare is a heterogeneous platform. It's very similar to like Grand Central Dispatch or some of the other methods that would be used to distribute in a queuing system, for example, workloads across a platform. Mare was developed by our corporate R&D and is actually being used in real products right now by various of our customers. The aim there has been to not necessarily impose a programming language, but offer an environment that would distribute the work across the different heterogeneous cores, including CPU, DSP, and GPU. In the case of GPU, the preferred language is to use OpenCL at this time. We haven't looked at doing anything else. But the real aim of Mare is to look at your workload and distribute it as evenly as it can. So it's an infrastructure for the developer. It's not magic. I like that it's not magic thing. It's not magic underneath. It's really it's a tool that you incorporate in and you program with and you develop on that makes the migration to different platforms much easier. But it's completely under your control. We don't try to do task stealing, anything. We just do whatever you tell us to do. And so it does still require some optimization, but the feedback we've seen on Mare has been, and you can check with Arthur. Is there an online for Mare? Do you know, Arthur? Like online documentation and reference code for it?
Yeah, actually Mare you can download Mare.
Oh, you can also get it from Qualcomm developer? Otherwise, email him with spam. But the idea is to create an infrastructure where you can develop code that will migrate to all these different devices and make it easier to migrate to the devices under your control.
Okay, I guess maybe one more question.
Don't ask me about Sickle.
So I find it difficult talking about performance and understanding the performance figures on mobile because the figures don't seem that high in terms of the GPU versus the CPU compared with what we're used to on PC. But then you also talk about throttling and whether that's including in the benchmark. So if I offload to GPU on a Snapdragon, is it only going to be 2 times as fast, or is it really going to be faster if you take into account that I might not want to burn through the pockets of my users? And is that going to increase over time?
There's a lot of questions
Sorry.
in there. No, it's okay. First and foremost, thermal throttling is reality. If you hit a certain temperature, we start throttling back the GPUs and the CPUs and the device to stay within, not to burn you. I mean, you can turn it off. But so it does happen. If you push the envelope of a mobile device, and you can push it over its thermal limit, it will hold you back. It's impossible for it to overheat. It's impossible for it to but it is possible for it to reduce your performance. Now, what I mean is all these numbers were measured on real devices, and were we thermally throttled in some of these cases? As far as I know, we were not. But it is certainly when we were running the CPU, we were likely to be. But on the GPU cases, we were not. Why? A lot of these use cases tend to be load store limited, and our bandwidth is far less in a mobile device than it is in a desktop, right? So I think somebody quoted something like 320 gigabytes earlier today. That's nice, but that's more than 10 times more than what we have. So you do have to derate. Our peak ALU in single precision is still 300 gigaflops or so, 300 something. On an 810. So it's fairly beefy, and our cores, our CPU cores are fairly beefy too. But if you turn them all on, for example, you'll definitely you could have an unpleasant experience. So it is always about performance in a power envelope, right? It's always going to be about that, and we won't let you get outside that power envelope, even if you try. So now, going back to your question on performance, I actually think in a real-world application running, getting over, in a single SoC in a mobile environment, getting 2 to 4x better performance per watt for a GPU versus a CPU is pretty freaking fantastic. Because when I used to work in the PC world, yeah, we would claim the kernel is 10 times faster, but the actual application is 20% faster or 30%. We're talking the application actually running 2x faster, right? So these are real frame rates with real video capture going on and actual processing of that and translating to a 2x performance advantage. So I actually do think that's good. Now, in terms of kernels on CPUs versus GPUs, it's very dependent. I can tell you if you did a pure ALU kernel, it's like a chain of FMADs, you're going to get drastically faster performance out of a GPU than you do out of a CPU. But if you're load store limited, and then how much is your overfetch on that, what's your cache sizes, you could find a CPU is faster than GPU in some kernels as well. DSP as well has certain properties that give it some advantages. So it's not always clear to me that, oh yes, the GPU will always be faster. I sort of like to think that, but it's not always true.
Okay.
Did I answer all your sub-bullets?
Okay. All right, let's thank our speaker again.